World Combinatorics on Words seminar. Our speaker today is Cor Kraaikamp from the Delft University of Technology, and he's going to speak to us about orbits of n expansions with a finite set of digits.
Yeah, well, thank you, Rad, and thank you all, also Manon, for inviting me to give a talk here. And of course, I always grab the opportunity to talk about continued fractions because I really love them, and yeah, that will happen until the end of my life, I suppose. So I have to warn you, though, that this will be sort of a superficial talk, actually, because there are many things to talk about, and also at some point it's not difficult, but rather technical. So I will skip all the technical details. So you only will get like an overview of what I did. Actually, it's not an old subject, but already many people have worked on this. For instance, I've worked with these people, Yu Fai Chen, who was a visitor here. He was at the time PhD student of Pengxia Li. And he was supposed to work on something totally different, but we worked on n expansions with finitely digits anyway, and with Karma, of course, many papers. And with Jaap de Jong, who was my PhD student, I wrote 2 papers together with Hitoshi Nakada, and of course, Niels, who sort of is responsible for starting this damn subject, I'm almost about to say, because it looks so simple and it's quite treacherous and difficult in the sense of it's never exactly what you expect it to be. But anyway, it's really a nice subject, and in particular, Jaap, he cannot get enough of it in a way. So, and of course, there's also Niels van der Wekke, who was what was he? He was a bachelor student of mine, and he and Karma and I wrote a paper on n expansions, but not just n expansions, not with finitely many digits. But I will explain a little bit what these things are, and then come gradually to n expansions with finitely many digits. But first, no, let me first say something about continued fractions, although probably you know this all very, so it's probably quite boring, but as you probably all know, every number x, real number, can be written in such a way. This R naught is actually the floor part or the entier part of x. And then if you do x minus R naught, it's a number between 0 and 1, and you can expand to a finite or infinite continued fraction, depending whether you're a rational number or a rational number. And if you're rational, you have 2 possible expansions, because 1 plus 1 is 2, and because of the Euclidean algorithm, really. And if you're infinite, if you're an irrational number, you have an infinite expansion, and yeah, then it's unique, at least as a regular continued fraction expansion. So this is very old stuff and extremely well known, and certainly, I suppose, to this audience. But already many things are known about this continued fraction, about the regular continued fraction. For instance, you have an underlying dynamical system with an invariant measure, which is the system is ergodic, or is even stronger mixing properties. And the invariant measure was found by Gauss. Nobody knows exactly how he found it, but he asked later. I think he found it in 1802, and in 1812 he asked Lagrange, like, I think it's the invariant measure. Can you show it? And can you also show how fast Lebesgue measure? Of course, he didn't call it Lebesgue because Lebesgue still had to be born, but how fast the Lebesgue measure, so the Lebesgue measure of t, the t nth inverse of some interval, how fast it converges to the invariant measure of that interval. And that was actually, well, in his letter, he says, for someone like you, this should be easy. I don't know whether he was cynical or not, but it took more than a century before this was actually proved independently by Kuzmin, and a year later by Lebesgue. And actually, Lebesgue gave a better error term, but okay. And this sort of led to many applications of this Gauss-Kuzmin-Levy theorem, and applications in the sense of how often do you see a certain digit in a continuous fraction expansion, or, well, many properties. And also this speed was sort of, for many years, like the subject of investigation. People really try to improve it, and then later in the 70s or 60s, Wielsing and Babenko, they came up with kind of final solution. After the Second World War, actually, a Polish mathematician, Rilnacewski, showed that the underlying system is ergodic. And with this, he sort of found all these results, but without, of course, the speed term. But he found all these results by Levy, Hinchin, you name them. There were many results, actually. So that was really nice. It's very elegant and fast. And actually, the remarkable thing is that Döblin, in a way, already knew this, that it was ergodic. And I will perhaps come back to this, but I'm not sure. Döblin already had many nice hunches about continued fractions. One turned out to be what was called the Lenstra conjecture and is now called the Döblin-Lenstra conjecture, which was proved, by the way, by 3 Dutch guys, one of which is my own advisor. And then actually in the proof of this conjecture of Döblin and Lenstra, one thing was very important is that you have a dynamical system, not a one-dimensional system like the one Rilnacewski looked at, but a two-dimensional system. So you need to have a kind of a future, but also you need sort of to keep track of where you have been. So you need to kind of have a kind of a past. And I still remember that my advisor once said, I worked on this problem of Lenstra and I couldn't do it. And other people worked on it, Knut, for instance, and they couldn't do it. And then I saw this paper by Nakada, in which the natural extension was sort of given or created or whatever you want to call it for the regular continued fraction. And then, and for Nakada's alpha expansions. And then he said, oh, wow, this is it. It's a system with a future and a past. And he could make things to work immediately. And they were able to solve this Döblin-Lenstra conjecture. Okay, this is for the regular continued fraction expansion. You could also do such things for alpha expansions of Nakada. There are other alpha expansions by Ito Tanaka. They're slightly more difficult, although the definition itself looks simpler. But yeah, somehow you run into more problems with that expansion. You can also look at other expansions. There are many other continued fraction expansions, Rosen expansions, complex continued fraction expansions. It's like a business in a way. You can sort of try your machinery on all of these guys. And some of them are easy and others are more hard. And also to see that they are interrelated is very nice. It's very nice to see that, for instance, these alpha expansions of Nakada, they have very nice structure, in particular when alpha is between 0.5 and 1. They're very closely related to the regular. Actually, the convergence forms subsequence of the regular, but you can do much more, also in the sense of ergodic theory. And for all of these things I've mentioned, there's one classical result. If you have a quadratic irrational, then the regular expansion is from some moment on periodic, and so eventually periodic, and vice versa. The vice versa is, of course, easy. And well, why do I mention this result? Because it's a very old result, a very nice result. Well, because this was like the starting point for Ed Berger, or I should say Edward Berger and his students in, well, I can't see the date because there's something blocking my view, but I think in 2008 or something. So what he wanted was to make a variation of the continued fraction expansion. Instead of, you do 1 divided by the digit plus 1 divided digit in a regular one. Well, he wanted to have an n, a positive integer or a negative integer, not 0, of course. And then divided by the digit plus n divided by the digit, etc. And why did he want to do that? Well, he wanted to show that for every quadratic irrational, you can find infinitely many of such n expansions for which the expansion is periodic, okay, not a big deal, but the period is 1. So it goes really fast. And so you have a very nice algorithm which gives you a subsequence of the regular thing, etc., etc. And actually, when I saw that, I had a bachelor student, and I said, okay, let's work on this. Because the reason why was that Berger and his students, they looked at these n expansions, but not using a kind of Gauss map, which for me is really a natural thing to do. It sort of ties you to ergodic theory. The map itself is very handy to work with. So I right away thought, okay, we could use this as a variation of the Gauss map, and this gives you an n expansion. But the nice thing about n expansions, the n here is a positive integer larger than 1. The nice thing about n expansion is that every x, almost every x, has infinitely many different expansions, which is surprising. And this one, so using this kind of Gauss-like map, if n is 1, it is the Gauss map. This gives you like a kind of greedy continued fraction expansion. You take the biggest digits, you like in this beta expansions, you really try to do it as fast as possible. You don't have to do it like that, but this is one way to do it. This was not looked upon like this by Berger, nor by another two guys who worked on this, Anselm and Weintraub. But they showed that actually for every x you have, apart from the thing of measure 0, you have that every x has infinitely many expansions. But they didn't use this map. Of course, this map has a special status also in their paper because it's the greedy map. And then you can say, okay, what can we say about if I use this map? Can I sort of get the results we have for the regular? Well, that turned out to be really boring and really easy. So you can say, if I use the greedy map, do I have an ergodic system? Yes. Do I have an invariant measure? Yes. What is it? Easily found. It's not so hard to find. It's really sort of a kind of exercise when you're in the train from A to B. You can do it almost by heart. So that was really too easy almost. You would say like, is this really something worth working on? Right? Well, I mentioned Anselm and Weintraub. They came up with a question or a conjecture rather that if you can choose a quadratic irrational and you can choose certain n's, and for some n's, that was proved by Berger and his students, you will have that it's periodic with period length 1. But how about other n's? And they conjectured that actually there are situations that a quadratic irrational will not have a periodic expansion. And that I found very, how to say it, very interesting. I must say, the student, Niels van der Wecke, and I thought about this before we read the paper by Weintraub, Anselm and Weintraub. And then I forgot about it and they published it and I thought, stupid, but okay, who cares? So yeah, what to do? And how can you see that there are more than one expansion? Well, what you could do is take your regular one and then multiply the numerator and denominator by n. And then at some point, no, I don't know if you noticed it here, but this n over x, its floor value, means that you get integers which are at least n or more. So this expansion, this greedy expansion, will have an expansion where the digits, the partial quotients, if you like, that kind of language, they are n plus 1 until, as large as you want. And so if you would start by multiplying the numerator and denominator by n, then at some point you run into problems. Let me show you. That's what you would get. This expression x would be r0 plus n over r, n over n times r1 plus n over r2, of course. And this is not. This might not be a greedy expansion. So let me show you. I think. Oh. I'm telling you a lot of things, but this is what I wanted to show you. So suppose I want to look at the 2 expansion, and this is just a simple number with regular expansion, 1 over 1 plus 1 over 2 plus 1 over 3, and then repeat it. So it's a quadratic irrational. And what you could do is multiply the first one, the first one in the numerator and the first one in the denominator by 2, and then you would get here 2 divided by 2, and then you would 2 times. So you would do it like this, 2 over 2 plus 2 over 2, that's still no problem. And here you would get 2 over 6 plus 2 times if I would do 2 times 1, I would get something which is inadmissible for the greedy expansion. That's not allowed. So this is the reason why I had a bachelor student. Well, these guys in Delft usually are pretty good in programming. So I told him, there is a really nice paper by a guy called Rainey, and he works with transducers. And can you make like a program in which there is a transducer? Right? So you do like 2 times actually the original number. And because the first digit, the first partial quotient is 1, we know we're between half and 1. So 2 times this number is between 1 and 2. So it will become like 7 plus 1 over something. And then I can do the same trick until I run into the same problem. I have to use the transducer again and then again and again and again, infinitely often. And well, this guy did it. Let me see this is what you would get, right? This is what I had, and then I would get 6 plus 1 over 1 plus 2 plus 1 over, etc. And then you do the same trick, multiply top and bottom by 2, etc. And then he calculated, I think, more than 70, it's written there, 70,825 exact digits of this new continuous fraction expansion of this irrational number, this quadratic irrational, which is regularly only 1, 2, 3, 1, 2, 3, 1, 2, 3. And by the way, this thing drawn here is the density of the invariant measure. So pretty weird and remarkable result, I would say. It starts to look pretty much like the density, really, which is sort of nice and surprising. Okay. So that's about n expansions. And well, with this Niels van der Wecke, we actually worked on something else as well. And then later with Niels Langeveld, we also looked at n expansions, but then we wanted to have a variable n on top of it. That really turned out to be a beast. I explained the continuous fraction expansion to several people, to Fritz Schweiger, for instance, who is really good at these things. And yeah, I mean, it's easy to see how it works. It's not so hard to prove it's ergodic. It's extremely difficult to find the invariant measure, although it looks a little bit like the regular density. And 1 over log 2 times 1 over 1 plus x. Well, the one if you have a variable at the n, and the n is steered by where you are in the interval 0, 1, then things become very hard. Okay, so that was work with Niels, and Niels and Karma and I published this. And then Niels wanted to do also a master thesis with me, but then he said, I want to come up with a subject, and actually already have a nice subject. He said, I want to work actually on, I want to shift the interval a little bit away from 0. So I don't want to look at 0, 1, and then the greedy expansion where you have infinitely many different possible digits. But if I slide it a little bit away, so let's say from alpha larger than 0 to alpha plus 1, then suddenly I can have only finitely many digits. And I thought, well, yeah, that sounds like a nice idea, probably not so hard. Yeah, go ahead. So he worked on it. Yeah, so this is the situation. I have an alpha which is larger than 0. I take it smaller than root n minus 1. I have a fixed n. I just choose some n and I fix it. And I take my alpha here. I don't want to take it larger than that, because then I would get partial quotients equal to 0. And somehow I find that unnatural. It's like your continuous fraction can sort of collapse a little bit. And yeah, doesn't feel right in a way. So I sort of limit it to root n minus 1. That's like the maximal value for your alpha. And well, and then we do like in the regular case. We say, okay, we look at n over x, and then we subtract the digit in such a way that we're back. N over x throws you out. And I slide back until I'm in the interval from alpha to alpha plus 1. You can actually say what this digit, this partial quotient, is supposed to be. And you can easily see there are only finitely many of them. And the closer alpha gets to 0, the more there are, actually. And so if you have an alpha which maximal, root n plus minus 1, then you don't have so many different digits, usually only 2. But if you slide alpha, let alpha go to 0, then more and more digits appear. And in the limit, if alpha is 0, then you are in the A greedy case, infinitely many. But we stay away from that because we want to have finitely many digits. Okay. And how do you get the expansion? Well, you have that the t applied to x is n over x minus the digit. So if you bring the digit to the other side and put things upside down, you get that x is n over the digit plus t applied to x, simply by putting things upside down. But then you repeat this, not to x, but to t applied to x. So this is replaced by n divided by d2, the second digit, plus t twice applied to x, etc. You can also do this for the regular, for any continuous fraction. That's why it's so nice to have a map. And then you get such an expansion, of course. You need to show that actually if n goes to infinity, it does converge to x, etc. That's not so much work. It's doable. And so you can look at the approximation. It's really bad. It's not a very, I mean, in the sense of quality of approximation, you don't want to use this thing. You want to use the regular or like the nearest integer or things like that, who really give very good approximation quality. This thing is sort of bad, but okay, it's also more like a toy. What can happen really, and can I understand what's going on, and why is the behavior? Well, we didn't know at the time, but why is the behavior so wild? Okay, so these digits are called partial quotients, or usual language for this. Okay, and you can do all kinds of standard things. You can see what are the fixed points, so which are points which have a periodic expansion, purely periodic expansion, and they're of this form. It's a trivial calculation. And of course, if you look at your cylinders, you time one cylinder, so where the digit is, let's say 1, 2, 3, whatever they are. These are sort of separated by this continuity point of your map. And well, these points can easily be characterized like this. This is all very trivial. And well, a lot of things I'm going to tell you will be from a paper in Monadshefte by Jaap de Jonge and by Hitoshi Nakada and myself, and also from another paper with a paper before that paper of Niels Langeveld and myself. And that's essentially what Niels did in his master work. Not everything, but essentially. Okay, but the paper, unfortunately, is very technical, not deep mathematics, but because the map is so treacherous, things don't work so well. Well, one thing which is easy is because we sort of take alphas between 0, not included, and root n minus 1 included, we see that the derivative in absolute value is larger than 1 on the interval, except if alpha is root n minus 1. So we have expanding maps, which is really nice. And so the fixed points really, if you are near a fixed point and you use your map, you sort of drift away. You go left, right, but the distance becomes bigger and bigger. That's a very handy property, actually. And well, some language, we call it a cylinder. So the set of all points with the very first digit equal to d. We call it full if this set is mapped to the whole interval from alpha up to alpha plus 1, and otherwise not full or incomplete or whatever you want to call it. And yeah, well, actually in already the Niels's thesis work, it was clear that things happen, particularly when alpha is close to root n minus 1. And in the beginning, if you take alpha, if you take n small, things are very nice. And yeah, the whole space, there's no holes, everything looks calm. And then after n is 9, suddenly things start to happen. And Niels made a lot of simulations, and then we were sort of, what's happening here? How can we understand this? And in particular, Niels for NS2 made a simulation of values of alpha and then the map, and then what is the entropy? Of course, it's like a kind of, it's really a simulation because we didn't know the invariant measure, but here you can see something which is remarkable. At some point, it was horizontal, the entropy, as a function of alpha. So I said to Niels, like, wow, are you sure it's really horizontal? He said, yeah, this is what my simulation shows. And then I thought, wow, but then actually the underlying systems for these alpha expansions, so for the values of alpha between this value and root 2 minus 1, these systems, we should be able to build an isomorphism between them. And that would sort of give the equal entropy. And actually, well, that's what we did actually. And well, I'm going to mention a few of the results, but I'm not giving the proofs, although they're not hard. But essential in the proof is something Niels has been working on since then a lot, not only, but a lot, and that's matching. And so you have the interval from alpha to alpha plus 1, and the endpoint starts to walk around in alpha to alpha plus 1. And when they meet, whenever they meet, then you can sort of use this to build a natural extension. I'm not giving you the details, but it's sort of not so hard once you have this. And it's actually a trick uh, I've been using for a long time. I've used it for instance, for Rosen expansions with Tom Schmidt and Bob Burton. And so once you have matching, and in that case you also have matching, then things are sort of nice. And yeah, part of what we have been doing is lately to look at situations when where there is matching or when there is no matching. Uh, and yeah, we have some results I will mention shortly. This was case NS2. Actually, this picture is not by Niels, although he has exactly this picture, but actually by Yufei Chen, because he also made for NS8, because we wanted to do what Niels did, or what Niels and I did in our paper. We wanted to do it for higher n. We wanted to know, are there like intervals where the entropy is the same? At first, a simulation, there's no proof, of course, and then we were sort of diving into it and finding intervals where really we can construct an isomorphism. I mean, then we really have the thing in our hands. And I don't know if you see it here, it's obviously horizontal, but there are a few other places, but it's actually quite hard to see for NS8. And in the paper with UFI, actually, I showed that for every n, we can find such intervals, such plateaus where the entropy is the same, but actually we found them only if we had matching in 3 steps from the left and the right, meaning you start with alpha and alpha plus 1, you apply t, your continuous fraction map 3 times, and then they match. And if you sort of demand that, then you can find the intervals we found, UFI and I. And but okay. But let's go back to the paper with Niels, because this is sort of a very nice paper because it's the easiest situation and it's already very informative. So this is the map where when alpha is maximal for NS2, so alpha is root 2 minus 1, and we have only 4 branches, and it looks like this. The first 3 seen from the right are full, and the last branch is non-full, and of course this sort of yeah, makes things more difficult. Okay, that's not so bad. And then so we wanted to construct a natural extension because that is really very successful, and it helps you often to find invariant measure, funnily enough. Just to guess it is much harder than to use a natural extension and then project on the first coordinate. And the first coordinate is just the ordinary map T, yeah? So the Tn map or the T alpha n map. And the second coordinate is like in the case of Jager and Bosma-Wiedijk, when they proved the Deuplin-Lenstra conjecture, is keeping track of what you have seen. And because this is the digit you just saw, and if you apply it again, this will sort of sink in the past, and you get more recent digits above it, so to speak, more dominating. And yeah, so this is really the past component. And of course, this is the future because it's a shift map. If you use T and you sort of dump the first partial quotient, A1 or D1 or whatever it's called, and you do N over X minus the digits. So it's out of the window, but it gets here. So that's why it's a beautiful system, because it keeps really track of future and past. And we wanted to build this. And actually, in this simple case, alpha is root 2 minus 1. For when we thought we would have we would be able to build an isomorphism. So actually, we just guessed it. It's not really a wild guess. I mean, of course, we have some experience with continued fractions. They still behave quite nicely for these values of n and alpha. And here you can see how the map works, how it sort of maps. This is the cylinder where the digit is 1, and it's mapped here. This is a cylinder, and the y, of course, yeah, is between some boundaries. And by sort of demanding then it goes to the same space and that there are no holes here, we sort of could calculate A, B, C. It's an easy calculation. And once you do that, I'm not going to do it for you now because no time, but it would give quadratic irrationals. Huh? So A would be root 33 minus 5 over 2, etc. And using this, we could guess the invariant measure. And by projecting on the first coordinate, we got the density for the one-dimensional map, the invariant measure, the density. It looks horrible. I mean, come on. But it doesn't matter. It's okay. And at the time we thought, oh, wow, are we lucky we could find one? But then we noticed, if alpha is in this region, and this is the region you saw in the simulation of Niels, where the entropy is horizontal, the same, for these alphas, actually, we have matching. So in 3 steps, the left endpoint and the right endpoint come together. And we could use that to actually, find the density and find the invariant measure and find the whole system. And then we got greedy because then we said, okay, then we want to show how to build an isomorphism. And the idea is actually very simple. We start with the case alpha is root n minus 1. And then we say, okay, we want to go smaller. So we slide off part of it, but that will create a hole and a hole. And of course, this is sort of moved there. It will be like your digit is by like increased by 1. So this is moved, and you can calculate how to move it. On the first coordinate, this is just a translation. And it's something I did actually also with the alpha expansions of Nakada. So it's not so difficult to do. So this one goes there. And by the new continuous fraction map, I think it's mapped there and then, oh no, sorry, there and then up. And then the magic happens because of matching. The holes and the new stuff sort of are on top of each other. So you might have a hole by sort of erasing this and then erasing that and then erasing this. And then you would get a hole inside. But lo and behold, because this is slid there in the new system, this goes there, up, and fills the hole. So you have a hole again, so to speak, but now with a W in front of it. So this sort of gives you a nice isomorphism between the two systems. And the nice thing is also that the measure is invariant because it's an isomorphism you build with the continuous fraction map. That's the great thing about it. So for these values of alpha and a little work, of course, I mean, this is just without details, we could prove that all these systems are isomorphic and have the same entropy. Okay, but Niels had several other very interesting simulations. For instance, this is something I mentioned. If n is growing, here is the alpha scale, n is 100. If your alpha is close to the maximal value, or is equal to the maximal value, so like root n minus 1, then actually, how should you read this? How should you understand this figure? Well, given an alpha, this would be the natural of the region. It doesn't work. But you would get a horizontal stripe. And if alpha is bigger, you get holes. So what does it mean? It means that if you start to walk around with your map t squared, t third, etc., there are parts of your space you might have been in and at some point will never come back to. Really like holes, really like empty spaces. The attractor is not the whole interval from alpha to alpha plus 1. And well, when we saw this, we thought, well, you can have at most 3 holes or 2 holes or 4, perhaps, I don't know. And I remember that I was in Pisa and Wolfgang said to me, nah, I don't believe it. I really don't believe it. I think there must be cases that you have many, many more holes. And of course, I think he had this knowledge from these negative beta expansions, if I'm not mistaken. But okay. And he was right. And we were wrong. We were sort of fooled by the simulation, which is very convincing. But the problem with simulations, of course, is that the holes become extremely small, much smaller than pixel size, so you don't see them anymore. But actually, recently in our second paper, Jaap de Jonge and I showed that the number of holes for alpha maximal, if n grows, is an unbounded non-decreasing sequence. So it actually, the number of holes become really crazily many if n goes to infinity. So yeah, and you don't see that, of course, in the simulation. So that's why I mean this is a very treacherous map. It's very hard to get a grip on it. What is nice is that if alpha is between some sort of value, it seems there are no holes at all. And that was actually the very first result Jaap and I and Hitoshi were able to prove. It was actually Hitoshi who said, well, if you're expanding enough, let's say if the derivative of your map is 2 or more, then it should work. You should get the whole interval because your map is really like pumping, it's sort of filling the whole space in a way. It wants to fill it. If you take any interval which is in a cylinder, okay, if you apply the map T to it, it might cross over one of these dividing points. So it might be in 2 or in 3 cylinders. Well, if it's in 3 cylinders, the one in the middle is always full. So then, wham, you will send it everywhere. But if it's in 2 cylinders, one of the 2 parts is larger than the original one. And then you use that, and you see it's like popcorn bubbling out of the thing, it has to fill the whole thing. And that's what we proved, actually, Jaap and Hitoshi and I. That was our first real result. And it right away explained why you have this solid green beam. And this was for n is 100 and just a simulation, but we could prove that. Okay, and just to see, why do you have a gap? So this is n is 100, root of 100 is 10, minus 1 is 9, so this is the maximal case. Well, note if I have, so the digits, there are only 2 digits, 1 and 2, here they're mentioned, this is 2 and this is 1. This interval from 9 to this dividing point, it's sort of turned around and stretched. So this P2 is mapped to 9. And 9 is, of course, mapped outside the interval because your map is expanding. So a little bit is sticking out. And if you look at the bit sticking out, so from the dividing point up to the T of alpha, then you know, oh, where is it going to? It's going to all the way the other end. The P2 goes to, if you use the digit 1, it goes to alpha plus 1. And of course, the image of alpha under T goes 2 times applied T to alpha, goes all the way here. It gets a little bit bigger, but not that much bigger. And all the points in the middle are not reached. You never get there because this guy goes back to this interval where you have digit only 2. Wow, that's spectacular because the map here on this cylinder is full. That means that all the points who are here around this fixed point, which is of course staying put there, but all the other points are drifting away from F1, from the fixed point, until they hit the cylinder of digit 2, and then they will never come to this hole again. So this is how you see how holes appear. And there also will be a hole around this fixed point, F2. So that's sort of easy to understand. So 2 holes is sort of easy to understand, but 3, 4, 5, 20, things become very, very complicated. And then, to be honest, Wolfgang was completely right. In the beginning, we thought there will be only finitely many. And when he told us, we thought, yeah, okay, Wolfgang, but we think it is finite. Well, we were wrong. He was right. Okay, so what is a gap? This is the official definition that you don't get there, don't get in there anymore after some time for almost every point. Okay, we were wrestling with the definition, but it's sort of an obvious thing. And then, yeah, we got all kinds of results on the digits, how large they are. Okay, well, you had to look at the case that a cylinder could consist of just one point. We had to sort of change the definition a little bit there because that's, of course, silly. Right? If your endpoint yeah, is mapped to itself, then yeah, that's a cylinder of just one point. That cannot be right. It should be mapped to the right endpoint. Okay, all kinds of weird things. And Jaap actually came up what is the branch number. So that's really the length of the branches, where the cylinders are mapped to. So if you have a full cylinder, the contribution to the branch length will be 1, and otherwise less than 1. And this turned out to be a very handy thing. I'm not going to go into details, but actually it was very smart of him to come up with this, I have to say. Okay. And then you could see, due to this, we always would have at least 2 cylinders. Of course, I mean, that's sort of obvious, but well, we have a proof of this. And also, you see many other things, that the branch number, the length of the branches, if n goes to infinity, actually goes to 1. So your whole space will be more or less empty, will be just one gigantic or more than one hole. It's like silence, like the end of time or something. No, whatever. And then, well, we had many, many results. So with Hitoshi, for n larger than 9 and the branch number larger than 4, no gaps, for instance. And if the derivative larger than 2, also no gaps in absolute value, of course. And yeah, all these kinds of results. If you have only 2 digits and the left endpoint is mapped to the right of the right fixed point, so you sort of overlap there. That means that from the dividing point up to this point, you contain the fixed point, and then if it also happens on the other side, then it's obvious you cannot have gaps because of the way the map moves. So yeah, these were low-hanging fruits, and there were some other things which were certainly not low-hanging fruits, and we worked on that for a very long time. The nice thing was that when Jaap did his PhD, the first 3 papers, PhD is more or less 4 papers here, the first 3 papers went very fast. So I told him, now let's do a little bit more dangerous stuff, and the dangerous stuff is really dangerous because he still works on this. I did his PhD years ago, but he's still working on this subject. So it's more than an addiction. I mean, people say you work always on continuous fraction, but at least at more than one kind. Sorry. Okay. And this is kind of a map or kind of, yeah, how did he call it? Spinner web, cow web. Jaap used that, so that here you can track the orbit of a point, and you can see how the gaps appear. So Jaap made very many of these figures just to understand what was happening. Okay, and yeah, well, another result. I mean, there are many results. I don't want to mention them all. Okay, and this is, for instance, alpha is f3, so this is a fixed point. So you have to actually map it to alpha plus 1 under the map. You have to change the definition, actually. And then you see there are really gigantic holes, gigantic gaps. Here is one, and there are 2 gaps, but they're enormous. So it's really very nice to work on this, to see what is really happening. Okay, and yeah, well, I can read this, but we had many results. Okay. Okay, so you can find arrangements, I already mentioned this, that you have a huge gap, but there might also be very many small gaps. And this is something we've been working on, Jaap and I, lately. And then you can see that, for instance, in these figures. And the phase transition, or the transition from one situation to another, is quite delicate. If you look at this is alpha is 1.87, and this is 1.868. So it's pretty close to one another, and the behavior suddenly changes enormously. Okay, so this is what I worked lately with Jaap, and before that with Jaap and Hitoshi. And yeah, actually Jaap is now working on the case that alpha is not maximal, and then see how you can control or how you can understand the number of gaps and things like that. Well, it's even more complicated and more bewildering, and actually it's actually yeah, sort of takes your whole mental power, at least I think so. Well, at some point in autumn 2022, Yufei was here for a year. He was a PhD student, as I said, of Wengsha Li, and he wanted to go to Australia because he wanted to work on something in control theory, of which I don't know anything. But Australia was at the time closed for everybody. I mean, even Australians couldn't return to Australia due to COVID. And then Wengsha said, well, why don't you go to Europe, go to Cor? So he came here. And then I said, yeah, sorry, but you know, I don't know anything about control theory. But if you want, we can work on a problem which is in my ball game. And this guy really picked it up so quickly. Incredible, really. This is a really bright person. Uh, and actually, we worked very well. And what we worked on was indeed this idea of matching. And so we started to force matching in 3 steps. He did many simulations. He's like Niels, extremely good at doing simulations, just to be steered by what's happening here. Can I see something? And then we were able to show that for every n, there are intervals where you have matching in 3 steps. And in this interval, you can actually build a natural extension due to matching, but also you can show they are isomorphic. And it's actually a kind of generalization of what Niels did in his thesis and what we did, Niels and I, in our paper. And this idea to move strips, I call this quilting. I used this long ago in a paper with Tom Schmid and Jonica Smeets, really long ago. This idea of quilting, that you sort of cut off parts of your natural extension and move them around and make holes, and then everything comes together. That turned out to be extremely nice. And yeah, in those situations, it looks, I mean, if you see the results, it looks like horrible. But when you see the pictures, you think like, oh, wow, it works well. It's nice. Okay, and then in a paper last year, by the way, the paper with U5 was accepted and will appear in a Japanese journal, but I forgot the name of the journal. Oei, that's stupid. Anyway, Niels and I again started to work on this. I'm very happy about that. And we actually finished it, and we were able to show that there are intervals of alpha where you have no matching. So that's really, in a way, an annoying situation, because you would like to have matching because it gives you easy access to build natural extension. And if you don't have matching, we have no idea what to do. So I mean, okay, this is the result. So it's a nice result, but in a way, it's a result which is sort of hurting us because we cannot do our usual machinery. Niels and I sent this paper to Ramanujan, and it was actually accepted last Saturday. So that's pretty hot off the needle, so to speak. I think it's a very nice paper. I'm not sure Niels is still there, but because he said he had to teach, but I think that was a very nice cooperation. Okay, I didn't give you any detail. I didn't give you any proof, only a lot of talk. However, this is what I wanted to tell you, just to give you like a review, kind of overview of what we've been doing. And if you want to know more, please read our papers or just contact me or Niels or Jaap or Hitoshi or Karma, because Karma also has a paper with Niels on N expansions. And well, any questions? Do you have any questions?
Oh, thank you very much, Cor.
You're
Yeah.
welcome.
Does anyone have any questions?
Well, everybody has pain in their ears now. Shall
Oh,
I
Jeff
stop
has a
sharing?
question. Yeah.
Yeah, I was wondering if there's any theorem known that's similar to Ostrowski for regular continued fractions. Let's say you fix the denominator 2,
Yeah.
Would there be any sort of a Straussky kind of theorem?
Well, we didn't look at that indeed, but I think we should be able to find that. Yeah, sure. Yeah, Ostrovsky or the Belgian guy. Yeah, definitely. Yeah. Yeah, this is something actually Carmen and I were quite interested in last year. Yeah.
The reason why I was asking is because then there might be some sort of analog to Sturmian sequences that would be very natural in terms of a Straussky-like representation or something like that.
Yeah, that's true. I didn't think of that. I perhaps should ask Niels this because he worked on Sturmian sequences related to N expansions.
Yeah.
But to be
Okay.
honest, I didn't read his paper. Sorry. But
Anyway,
it's a very good question. Yeah. Very natural question. Yeah.
Thanks.
Yeah, sure.
Yeah, are there any other questions?
Too much noise.
Well, if not, thank you again. Thank you so much.